Okay, people are still joining, so we'll give it a couple of minutes. Can I just check that the audio is coming through and everyone can see the slides?
It looks and sounds fine to me.
Excellent, thank you. Okay, so the rate at which people are joining seems to be slowing down, so I guess we'll get started. Welcome everyone to the final session of the IETF109. Sadly not in Bangkok. I hope the time zone for you is not too painful wherever you are. I realize it's not great for some of the people, but I hope you've survived the week in whatever time zone you're on, and I'm looking forward to some interesting talks to finish up. This is the IETF open meeting. My name is Colin Perkins. I'm the IETF chair. So to start up, we have the usual note well, the intellectual property statement. Just a reminder that anything you say in in the mic line or in the chat is covered by the Note Well disclosures. Please pay attention to that. I'm sure you know the rules by now. In addition, we have a privacy policy and a code of conduct. Be aware that the meeting is being recorded, and I believe it's being streamed live on YouTube. So anything you say may be public and may be recorded. In addition, we have the code of conduct, the anti-harassment policies. So please be respectful in the discussions. So this is the IETF open meeting. The IETF is a parallel organization to the IETF, which focuses on longer-term research issues related to the internet. Unlike the IETF, the IRTF is not a standards development organization. It does research rather than developing standards. And while it can publish experimental or informational RFCs, the primary goal of the IRTF is to promote development of research, promote collaboration and teamwork, and to try and get the research community and the engineering community, the standards community, talking to each other. If you're not familiar with the work of the IRTF, RFC 7418 gives a really good primer targeted at IETF participants. If you want to find out about what we're doing, the IRTF.org website has pointers to all the materials and all the research groups. We're on Twitter, we're on Facebook. We have an announcement mailing list, which is pretty light traffic. And we also have a discussion list if you want to talk about any of the topics. Plus each of the research group lists has research groups has its own mailing list, Jabber Room and so on. IETF is organized as a bunch of research groups. There are 14 research groups currently chartered. Those which are highlighted in blue on the slide met this week. We also have interim meetings for some of the groups coming up. The information-centric networking group has a meeting scheduled for I believe, the 1st of December. The privacy enhancements and assessments research group was also talking about having a meeting in December focused on IP address privacy, if I remember correctly. And I think there was some talk about the thing-to-thing research group also having a meeting, although I'm not sure that's been confirmed. So look out for those coming up over the next month or two. Comment in the chat. Gaia did not meet this time due to the conflict with the Internet Governance Forum. So yes, sorry about that. That's a mistake in the slide. We've also had 4 recent RFCs published on the IRTF stream. A couple very recently. The Crypto Forum group published an RFC talking about randomness improvements for security protocols. The information-centric group has an RFC looking at research directions for information-centric networking in disaster scenarios. And there are a couple of earlier RFCs earlier in the year, again from the ICNRG, looking at deployment considerations, information-centric networking, and some terminology. The Crypto Forum group has a draft on the Argon 2 algorithm, and the network coding group has a group on network coding and satellites, which are working their way through the process, and I expect they'll be going to the RFC editor very shortly, so to look out for those anytime now. In addition to all the research groups, we run, in conjunction with the Internet Society, we run the Applied Networking Research Prize. The ANRP is awarded to recognize the best recent results in applied networking, to recognize interesting new results and new ideas of potentially of relevance to the internet standards community, and to recognize upcoming people that are likely to have an impact on internet standards and technologies. In particular, we've got to focus on bringing in people or ideas that will perhaps not otherwise get much exposure to the IETF, the IRTF community, and perhaps not otherwise be able to participate in the discussion. The ANRP works as a sort of annual nomination cycle, and then the talks happen spread over the IETF meetings in the coming year. The nominations for the 2021 awards are open. The deadline for nominations is the 22nd of November, which is this Sunday. So if you know of any good applied networking work, any interesting people, any interesting new ideas that it would be worth bringing into the IETF, the IRTF, and that you think would be suitable for this prize, then please go to the irtf.org site, irtf.org/ANRP, and fill out the nominations. We encourage self-nominations if you think your work is appropriate for the prize. And that brings us to the main focus of today's meeting, which is that we'll have 3 ANRP prize-winning talks today. The first of these will be from Debopam, who will talk about his work designing network topologies for low Earth orbit satellite constellations. Georgia will be talking about her work on internet transparency. And finally, Ranisha will be talking about congestion control fairness. And with that, I'd like to pass over briefly to Matt Ford from the Internet Society, who I think wishes to say a few words to congratulate the winners. Matt?
Thanks very much, Colin. I hope everyone can hear me.
Yeah, a little quiet, maybe.
Maybe that's better.
Yep.
Yeah, I just wanted to briefly say that it's a real honor for the Internet Society to be able to support the Internet Research Task Force in delivering the ANRP. It's certainly one of the most interesting and enjoyable parts of my job. And whether in person or virtually, I always think that ANRP talks are a highlight of the IETF week, and we've got 3 great talks coming up today, and it's great to see so many people online. I know what is a fairly unpleasant hour for some to hear these talks, so that's great to see. I just wanted to say that we have had long-standing support from Comcast and NBC Universal to help us in supporting the prize. If you work for an organization that thinks this is a great initiative and would like to see your name on the list of sponsors for the ANRP, please don't hesitate to get in touch with me. Thanks very much.
Okay, thanks, Matt. Thanks again to Comcast and NBC Universal for sponsoring this, and congratulations to the winners. And so with that, the agenda for the rest of the meeting will be the 3 prize-winning talks, starting with Debopam, then Georgia, and then Ranisha. So the first talk, and if Mitaka can get the video ready, the first talk will be by Debopam, who'll be talking about network topology design at 27,000 kilometers per hour. Debopam is a 5th-year PhD candidate at ETH Zurich, and I understand he'll be on the job market soon, so if you like this work, please chat to him afterwards. His work focuses primarily on low latency network infrastructures, both terrestrial and satellite. The work on topology design he presents today was published in ACM Conext 2019 and is one part of his work on new space satellite networking. Okay, Mitaka, if you can cue up the video.
Welcome to my talk on how to design a network topology when its components are moving at speeds of 27,000 kilometers per hour. Let me start by touching upon 3 fantastic recent advances in space technology. Reusable boosters, which come back to Earth after launching rockets, thus reducing launch costs. Significant reduction in size and weight of satellites, thereby packing more satellites per launch, reducing costs. And automated link tracking, which enables inter-satellite laser communication. Products offering laser inter-satellite connectivity at 10 to 20G at distances up to 8,000 kilometers are already available. One caveat is that it takes a few seconds to tens of seconds to establish these laser ISLs. This will later be important when we discuss the various topology design challenges. But what are all these developments leading up to? The primary goal is to build mega constellations consisting of thousands of low-flying satellites which provide global low-latency internet coverage. SpaceX is leading the front. Their project is named Starlink and they have already deployed more than 800 satellites in orbit. During the first phase, they plan to deploy 1,600 satellites and start providing internet coverage. Their long-term plan is to deploy tens of thousands of very low-flying satellites. Amazon is working on a similar project named Kuiper and plans to deploy more than 3,000 satellites in 3 phases, with each phase having slightly differing configurations. Various companies and startups have joined this race and have their projects at different levels of maturity. We here explore how to connect satellites with each other in order to build such networks and deliver traffic effectively. But before we discuss topology design, we'll go through a primer on constellation design, followed by discussions on the challenges of LEO networks and the utility of ISLs. First, a brief primer on the proposed satellite constellations is necessary to set the context. How do we describe a constellation? And what features distinguish this setting from traditional terrestrial networks? The first descriptive parameter I'll mention is altitude. A geosynchronous or geosatellite has a height of 36,000 kilometers, and the minimum round-trip times, or RTTs, are nearly 240 milliseconds. Low Earth orbit or LEO satellites, on the other hand, fly at heights between 300 and 2,000 kilometers, thus reducing RTTs by more than 60x. Another descriptor is orbital inclination. Each orbit here has several satellites. While polar orbits travels over the poles, orbits can also be inclined. Inclination is the angle between the orbit and the equator. Here, the inclination is 53 degrees. Inclined orbits restrict satellites over densely populated lower latitudes. For polar orbits, the inclination is 90 degrees. Laser or radio links can be used between satellites, with laser offering higher data rates. Typically, there is a north-south, east-west connectivity pattern, which I will refer to throughout as plus grid. To the best of our knowledge, all publicly available scientific papers, patents, and visualizations assume the same plus grid connectivity. A key feature of these constellations' promised connectivity is lower latency over distances beyond a few thousand kilometers. In this example, we are seeing a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being 2/3 in fiber compared to free space means that the fiber path will be 3x higher latency. We will refer to this inflation over geodesic, in this case 3x for fiber, as stretch. We compared the RTTs between the 8 most populous cities over today's internet to the estimated RTTs over a plus grid constellation consisting of 1,600 satellites. The estimated RTTs are 70% lower than today's internet at the median. So, if the current RTT is 100 milliseconds, the estimated RTT is 30 milliseconds. The estimates for the satellite network are a bit optimistic, as we did not consider latency inflation due to encoding, error correction, and other factors. But even a 20% increase in the estimate would result in an RTT of 36 milliseconds, which is still significantly lower than today's internet. We could also see from the plot that the latencies over satellite paths are very close to the geodesic latencies at the speed of light in vacuum. Let us now explore the system dynamics of these constellations. Satellites move very fast related to the Earth and with respect to each other. If a satellite is now over eastern Brazil, in 6 minutes, it will already reach Africa, crossing the entire Atlantic, traveling more than 500 kilometers per minute. Such highly dynamic behavior translates to links becoming infeasible in minutes. We should keep this in mind while exploring topology design and prioritize links which are available for longer periods. Having gone through the primer, let us now look at some of the challenges that arise due to the scale and extreme dynamicity of these mega constellation networks. Our work at ACM Hotnets 2018 discusses the opportunities and challenges of these networks in further details. Of course, topology design is a challenge. How do we define the trajectories of the satellites and set up inter-satellite links in order to serve the geographically distributed population? The various objectives, constraints, and challenges and geographically varying demands make topology design a high-dimensional optimization problem. We do not yet know whether the Starlink constellation is the optimal solution to this. Let us now see an interesting implication of a satellite autonomous system, or ACE, on BGP routing. Each of the 4 terrestrial ACEs, ACE1 through ACE4, pair with the satellite ACE, which is ACE-SAT. ACE1 has 2 equal ACE-length paths to ACE3 through ACE2 and ACE-SAT. The geographic distances could mean that where ACE is choosing routes based on latency, ACE1 should prefer the terrestrial route to ACE3. Likewise, ACE2 has 2 similar paths to ACE4. ACE2 should ideally prefer the satellite route to ACE4 in order to lower the latency. While it is already the case that ACE path lengths in today's internet are poor proxies for performance, these satellite networks may make this discrepancy larger in magnitude and more commonplace. Let us now see how routing can be made weather aware and what can be the implications. Imagine this is the path through which data is delivered to the destination. Cloud cover can introduce significantly higher loss rates based on operating frequencies. One approach to deal with this problem is to reroute network traffic around such cloud cover. This results in lower loss rates, but can increase the aggregate stretch of the network due to higher latencies. Let us now look at congestion control challenges. This graph plots the time-varying latency between the 2 locations for a period of 2000 seconds at a granularity of 1 second. Even recently proposed congestion control schemes like PCC Vivace, BBR, or COPA do not account for such variations in latency. They either assume end-to-end latency to be fixed or try to estimate the minimum latency to be the smallest seen over the last few round trips. Any additional delay is considered as a mark of congestion. Note that such delay due to path latency and path changes is highly predictable in satellite networks. Also, frequent path changes result in packet reordering, thus affecting even loss-based congestion control schemes. Having gone through the general challenges, let us quickly touch upon the utility of laser ISLs before we start discussing topology design. Our work at ACM Hotnets 2020 discusses the benefits of having ISLs in further details. Despite the high bandwidth, low latency ISL promise, there is substantial uncertainty about whether or not LEO constellations will successfully incorporate ISLs. One hurdle may be the burn on re-entry requirement that regulators are asking operators to satisfy, thus not risking injury and damage from deorbiting satellites. In response, Starlink's filings were amended to exclude mention of these components. None of the hundreds of already deployed Starlink satellites feature ISLs. Luckily, LEO networks do not need ISLs to provide service. One might think how to achieve long-distance end-to-end connectivity when there are no ISLs. Remember, as the constellations are being rolled out, ground terminals would also be rolled out. These terminals include user terminals on land and those mounted on airplanes and ships, and also more powerful ground stations. Without ISLs, connections between far-separated ground terminals bounce up and down between satellites and on-path terminals, yielding a bent pipe or BP connectivity. Latency lower than terrestrial internet can be often achieved over long distances even with this restricted BP connectivity. A paper in Hotnets 2019 focuses primarily on such latency benefits. However, in our work, we quantitatively show that even with dense ground station deployments, there are 3 very significant downsides to foregoing ISLs. Although LEO networks without ISL still provide low latency between many ground locations, the temporal variation in latencies increases substantially. The network-wide throughput decreases heavily, and the network becomes more vulnerable to weather disruption because of transit through satellite ground links. In-depth quantitative analysis of these downsides are in the paper in case you are interested, but to give some brief insight, let us touch upon temporal latency variations and impact of weather. With BP, the path between Maceió in Brazil and Durban in South Africa, for example, sees an inflation of 100 milliseconds over time. This is because the density of air traffic is much sparser over the South Atlantic than the North. Hence, the path often ends up using aircraft flying over the North Atlantic as intermediate hops. Note that this behavior not only inflates the RTT of this path significantly, but also makes the heavily used paths over the North Atlantic even more congested. By virtue of inter-satellite links in a dense deployment of satellites, such latency variations get reduced by as much as 80%. The impact of weather would be significantly higher on BP connectivity than on ISL connectivity. For paths consisting of ISLs, this value is either the first or last hop attenuation, whichever is worse. But for BP paths, this is the worst attenuation seen across all lengths of the zigzag path bouncing between the satellites and GT. In this example, the heat map depicts the 99.5th percentile attenuation across Southeast Asia. Although both endpoints, Delhi and Sydney, are in low attenuation areas, BP ends up using intermediate hops in regions with higher attenuation. In contrast, the ISL path avoids this entire high attenuation region. There are various other benefits of ISLs which BP struggles with, which I briefly touch upon. BP connectivity between certain sources and destinations is bound to require GTs in countries and regions that an operator would like to avoid, either because of challenging topography or due to political reasons. Ka and Ku band radio spectrum for the up and down links needs licensing. In contrast, thanks to the narrow beams and negligible interference issues, intersatellite laser connectivity is unlicensed. GSO satellites fly above the equator and operate in the same frequency bands sought for LEO communication. Thus, LEO satellites, when crossing the lower latitudes near the equator, must avoid interference with GSO satellites. While GT field of view is already restricted by the minimum angle of elevation, GSO arc avoidance makes this field of view even more restricted. The impact of this will be much higher on BP than on ISL connectivity for traffic between the northern and southern hemispheres. Here is the latest update on the status of ISLs. In the September 3 launch video, a SpaceX personnel announced the testing of laser ISLs in LEO. But a lot of uncertainties regarding ISLs still exist. What would be the link capacities in practice? Link setup is constrained by the fact that it takes a few seconds to tens of seconds to establish laser ISLs. How do we connect satellites using ISLs, keeping in mind these constraints? This is what we discuss next. Such analysis is also relevant for constellations like OneWeb, which do not plan to incorporate laser ISLs. Okay, having gone through general challenges and the utility of having ISLs, we come back to the problem at hand. So how can we connect satellites in order to offer higher aggregate bandwidth, keeping in mind the dynamics of the system? This work was published at ACM CONEX 2019 and is the main focus of this talk. I'll now discuss what are the constraints we consider and assumptions we make. The key constraint of this system is system dynamics. Satellites flying fast relative to the Earth and to each other. But we have other constraints as follows. Setting up links can take a few seconds to tens of seconds, during which time the involved communication units cannot transfer data. Hence, it's important to minimize changes in which links are connected. Also, the maximum number of ISLs per satellite is limited. In our work, we consider 4 ISLs per satellite, following all recent FCC filings, but we believe our methods can be extended for other numbers. I'll also lay out the assumptions we are making in solving the intersatellite topology design problem. We assume that the satellite trajectories are given. We rely on FCC filings by SpaceX and Amazon that describe their trajectories. While trajectory design in itself is an interesting question, we have not explored it in this work. Knowing what precise traffic will be served on these constellations is difficult. Our evaluation uses traffic matrices drawn from intuition, but the same approach can be used for arbitrary input traffic. Our focus is on the satellite-to-satellite connectivity. So we assume that the ground satellite connectivity follows a simple range-bounded model. We treat plus grid connectivity, which I already touched upon earlier, as our baseline. On the last point, plus grid being the baseline, what are we trying to improve? One drawback of these very local links to adjacent satellites is that one requires a large number of hops to reach distant destinations. On each hop, the end-to-end communication consumes resources, limiting the network's throughput. We would thus like to build networks that give short paths, but also admit high capacity. We don't need to stick to plus grid's very local links. The key constraint on ISLs is for them to not dip into the mesosphere. This is the atmospheric layer that extends to about 80 kilometers above the Earth's surface, beyond which there is no water vapor present. Given the altitude of satellites, in this example 550 kilometers, using simple geometry, we can calculate the maximum permissible ISL length, that is about 5,000 kilometers here. This observation opens up a large design space. While at small scale, with few tens of satellites, only simple connectivity was possible, in the large proposed constellations, each satellite can now reach many more satellites. We are still restricted to being able to connect to only a few though, limited by the maximum number of ISLs per satellite. In picking the particular subset of links to connect, what should we optimize for? We use simple intuitive traffic matrices for our evaluation. We pick the 1,000 most populous cities and use a population product traffic matrix. Let CT1, CT2, and CT3 be 3 cities with different populations. The traffic between city pairs is proportional to their population product. We also tested a variant which relies on GDP instead of population. Recall that I earlier mentioned stretch and hop count. Stretch is the inflation in latency over the minimum possible, that is traveling the geodesic at the speed of light in vacuum. Hop count accounts for resource consumption and hence congestion. In our paper, we show that lower hop count actually translates to less congestion in these networks. We also define an aggregate metric as a linear combination of stretch and hop count, with alpha being the weight or importance of stretch. Superficially, this seems like a traditional network topology design problem. These are known to be hard, even in static settings, but a variety of heuristics are used in practice. One key contribution of this work is showing why traditional techniques don't work here. We tried integer programming, but it suffers from 2 major shortcomings. It is limited in scalability. Runtime is greater than 2 days, even for 25 cities on a beefy machine, and the estimate is roughly 10 to the power of 29 days for 1,000 cities. But even if we manage to speed up the ILP by a large factor or use appropriate approximation techniques, there is a more fundamental issue here. The set of ISLs, minutes apart, are more than 90% different. We should remember that ISL setup times are few seconds to tens of seconds. So even if we could solve the problem optimally for a snapshot, the set of optimal links varies significantly minute to minute. Hence, to maintain optimality, the system would need to break and make a lot of links continually, resulting in significant disruption of connectivity. We also tried random graphs as they're shown to be useful in other settings like data centers. Although such random graph generation is faster, it also suffers from large number of links becoming infeasible within a few minutes. Regaining lost connectivity is not straightforward, and one would have to break and make many links. Additionally, random graphs are very inflexible and do not allow the operator to decide on the operating point. They simply yield one combination of stretch and hop count without any control over which dimension to optimize for. So where do we go from here? This, and this picture have something in common. They illustrate the use of structure and repetition for design, in this case, visual design. We apply the same idea of repetitive geometric structure to network topology design. Consider this 1600 satellite constellation. This is the field of view or connectivity for one satellite, which goes beyond plus grid. A motif consists of two links with two other satellites, and this pattern can be repeated throughout to build the network. Note that in this case, two link motifs are sufficient, as remaining two would be filled by other satellites connecting to this satellite. One obvious benefit of using motifs is the fact that they have minimum link churn. Nearby satellites in adjacent orbits move together and are always in the field of connectivity of each other and can remain connected continually. We have analyzed three different constellations: a uniform constellation consisting of 40 orbits and 40 satellites per orbit, operating at an inclination of 53 degrees and an altitude of 550 kilometers. SpaceX Starlink Phase 1, which consists of 24 orbits with 66 satellites per orbit, operating at an inclination of 53 degrees and an altitude of 550 kilometers. And Amazon Kuiper Phase 1, which is again a uniform 34 squared constellation, operating at 51.9 degrees and 630 kilometers. Here, we plot the average hop count along x-axis and average stretch along y-axis for the different motifs. Note that both stretch and hop count are weighted by the traffic matrix, in this case, population products for city pairs. Different motifs offer different trade-offs in stretch and hop count, and we can see a Pareto frontier of motifs superior to the rest in both hop count and stretch. Not only do motifs offer performance better than random graphs, they also provide higher flexibility to an operator. Note also that the random graph solution also suffers from link churn. So where is our baseline plus grid in all of this? This is where plus grid operates, with the best available stretch, but very high hop count, thus being a low efficiency motif. Note that the slope of this frontier is small enough on the right side, such that by sacrificing 2% stretch, one can improve hop count by as much as 32%. This is one of the resulting motifs for the 40 squared constellation that provides much higher efficiency than plus grid using a combination of long and short links of different orientations. I am showing the two links in the motif in different colors here for clarity. So the motifs perform well, but can we do even better? Yes, by exploring the geometry of these constellations. Compare the field of view of a satellite at the equator to one at a higher latitude. We see the constellation is denser at higher latitudes. This translates to more options for connectivity as we go higher up from the equator. This plot quantifies the number of motif possibilities at different latitudes. For polar as well as inclined constellations, the number increases significantly with latitude. For example, for the inclined constellation, there are around 1,000 options at the equator versus around 3,500 at higher latitudes. So how do we exploit this characteristic? Consider a single orbital plane. A quadrant of this orbit consists of 10 satellites out of the 40 in total in this orbit. We split the quadrant into multiple zones, 3 in this case. First, we find the optimal motif for the entire constellation, considering only the motif choices available at zone 1. Then, keeping zone 1 links fixed, we remove the rest of the links. We repeat the same process for zone 2 and then for zone 3 and arrive at the 3-zone multi-motif. This is the final 3-zone multi-motif scheme for the 40 squared constellation we are looking at. As you can see in the plot, the multi-motifs offer a higher performance beyond the single motif frontier. Different alpha values result in different multi-motifs. And as we give higher priority to stretch, the schemes move towards plus grid. Putting all of this together, these are the performance improvements above the baseline plus grid connectivity. Starlink sees more than 2x improvement over baseline, while Kuiper also has similar benefits. We also considered settings where the links need to be shorter due to power constraints instead of just the visibility constraint we considered thus far. In the most pessimistic case, a constellation must at least allow link lengths that suffice for plus grid connectivity. Even in this worst case scenario, Starlink sees a 40% improvement over plus grid. I'll briefly note that this work is just one of several satellite networking problems we are exploring in our lab. So now I touch upon some of the open questions we are trying to attack. How do we design satellite trajectories in order to improve network performance? There are various dimensions to explore, including the number of shells, orbits, satellites per orbit, inclination, and elevation. We are working on routing and congestion control challenges, as I briefly touched upon earlier in this talk. To help bootstrap research in this area, we are actively developing packet level and flow level simulators that capture the necessary system dynamics. With that, I thank you for your attention. And now I'm open to take questions.
Okay, thank you, Deborah. That was an excellent talk.
Thank you.
Does anyone have any questions? Okay, Jonathan.
Hi, good morning. Does it, so when you say routing and congestion control, is the idea that you would send traffic on a longer route over less populated areas just to avoid other traffic?
Yeah, so that's a very good question. What we have seen is, like, of course, when it comes to routing congestion control, if we send packets along just the shortest paths, it doesn't work. It's very inefficient in the sense that it congests some areas of the network heavily. For example, imagine all the traffic between North America and Europe using links over Northern Atlantic. So these links will be heavily congested. So of course, we will be needing some sort of spreading traffic, like K shortest path is something that comes to my mind immediately, which can actually spread the traffic more. But beyond that, what is interesting when it comes to intra-domain routing is, like, because the network is moving. So this is unforeseen. This has not happened in the past much, that the network nodes are moving at incredibly high speeds. So what happens is, like, the expectation would change. So as the link moves away from a set of paths, it would start catering to new paths as well, right? So even if you try to kind of send optimal traffic via some paths, those paths would see the link utilization, the individual link utilizations changing over time as the links scatter to a different set of end-to-end paths. So this is also very interesting. And what can be done here possibly is that given satellite trajectories are known in advance somewhat, so this dynamicity is kind of predictable in advance. So that advanced knowledge can be applied in order to shift traffic from links which are going to become more congested in the future.
Super interesting. Thank you.
Okay, great. Thank you. Rod?
Echo the comments of other people in the chat there. This is a really good talk.
Thank you.
I think you addressed this question in the talk, but I'm not sure I fully caught the answer. So you were talking at one point about variability in the path latency done terrestrially, but of course that variability, the physical path itself, the latency is actually fixed. The variability comes from queuing delays and traffic competition. But I'm not sure I caught how much you were modeling that along the satellite path, because the satellite paths, I think, are lower total bandwidth, and so they're actually potentially vulnerable to congestion at some point as well, right? Or lower link bandwidth. I'm not sure if the aggregate is actually lower or not.
Right. So I agree to that. When it comes to the, by that I mean that I agree that this variability in case of satellites, in case of paths usually come from queuing and congestion, but in case of satellites, it also comes from the fact that the links are changing. The link lengths are also changing continually, and there are often path changes as well. So when it comes to the topology design work, that was the main focus of this talk. We were sticking to the path length. So this is just propagation delay without considering any queuing delay or something when we compute the latency and the variations thereof. The variation I talked about was in a more recent paper, which was published in Hotnets 2020. But beyond that, so there we kind of quantified what the impact of foregoing ISL is. Like if you just use main pipe connectivity, that increases the variation of these end-to-end latencies. But beyond that, what we are doing now is like we're trying to understand this impact of variability when it comes to endpoint congestion control. So there are two aspects to this. Number one is like the link lengths are continually changing, because even if the satellites which are having inter-satellite links between them are moving together, because of the Earth's geometry, they come closer at higher latitudes and go far away at lower latitudes near the equator. So the link latencies are continuously changing. That's number one. And number two is like the paths would change as well. So as paths become more and more inefficient, after a while, the end-to-end traffic would need to use different paths. So these path changes are also frequent. So these two actually impact endpoint congestion control heavily. So, so we have to understand, like, this is not really congestion. These are changes that are expected, like path changes and path latency changes, but this would still impact congestion control if not handled properly.
Okay, and so the work in your paper was an apples to apples comparison of not considering the traffic congestion for both the terrestrial and satellite.
So so when I talked about path variations, like variation in latency, that was the Hotness 2020 work where we compared bent pipe connectivity and ISL connectivity, right? So what happens if a constellation has ISLs versus what happens if it doesn't have ISL? So there we had this apple-to-apple comparison, right? But when so when I was explaining the plot where we compare internet latency, that is the ping latencies from Wonder Network data, to satellite latency, there we give some sort of edge to the satellite network. So there, the internet latencies, of course, were also affected because of congestion and stuff, but satellite was just propagation delay. But if you see the difference is in latency, end-to-end latency is almost 70% at the median. So even if there is some overhead incurred due to end-to-end or even link level, like modulation, encoding, and error correction and stuff, that would that inflation would still be, if we consider that inflation, the end-to-end latency would still be significantly lower than today's internet. That's the expectation. Now, of course, I mean, when we bring in queuing and congestion into the scenario, things will be more interesting. But we are trying to simulate that. So at the moment, we are building a packet level simulator, and we already have a paper out. So this simulator can simulate entire constellations and cross traffic. So there we are also getting some interesting results, which arise due to cross traffic and the congestion thereof.
Okay, thank you. Is there any other questions? I don't see anyone else in the queue.
If you don't have anyone else in the queue, I actually have a second question, but I was going to defer that.
We've got a couple of minutes, so go ahead.
So the topic that I brought up in the chat, which you already partially answered, about the intercity traffic model, is that model original to you, or is there a reference to that? I've downloaded your paper, but I didn't find a reference in the paper yet.
Yes, so finding the right traffic matrix was difficult because, you know, when it comes to satellite networks, we should also address the temporal changes in traffic demands. So this we didn't do. We were sticking to very simple traffic matrices. So that's the reason we just picked this population traffic matrix and the GDP traffic matrix, and then stick to the gravity model, which is the population product, and the traffic demand is proportional to that. But you know, I mean, this tool, whatever we built in the context of this work, it can be used with any arbitrary traffic matrix. Of course, we didn't do any like more sophisticated ones where we also considered the temporal variations. But these are the traffic matrices. These two are the ones that for which we have results.
So the product of city population is equivalent to the gravity model?
So
I'm not sure.
yeah, I mean, I guess so. So there is another variant of it where we also consider the distance between city pairs, but and the product and the demand is it gets reduced as the distance increases. But this is one reasonable traffic matrix which have been used in the past. I mean, in a couple of different papers. I can offline send you a couple of references.
Great, thanks.
Okay, great, thank you. Excellent talk, and a reminder to everybody that, as I said at the beginning, that DEPUPAM is on the job market soon. So thank you, Deborah. Next up is Georgia, whose talk is about morphing packet reports for internet transparency. Georgia earned her diploma in electrical and computer engineering from the National Technical University of Athens, and she's currently a fifth-year PhD student at EPFL's Network Architecture Laboratory, where she's co-advised by Katerina Agaraki and Brian Ford. Her research focuses on enhancing trust around the performance of network systems and its implications for user anonymity and the privacy of network topologies. Okay, Mitoko, if you're ready for the next video.
Hello. Today, I will present to you our work on reconciling anonymity with internet performance transparency. This is joint work with my supervisors at EPFL, Katerina Agaraki and Brian Ford. In today's internet, when packets are lost or delayed beyond expectation, there is no systematic way to identify the network where the problem has occurred. This has important implications to network users. First, users cannot check whether internet service providers meet service level agreements. For example, if an ISP honors a less than 1% packet loss promise. Second, users cannot check ISP compliance with neutrality regulations. Consider the scenario on this slide where a broadband ISP receives all traffic, this is video streaming traffic originating at Netflix, and other traffic through the same interdomain link. At some point, Netflix streaming quality deteriorates due to large delays, begging the question, why exactly? This results in a peering dispute similar to the one between Netflix and Verizon. Netflix blames the ISP for discriminating against Netflix traffic, while the ISP says, I am doing nothing wrong. It just so happens that the interdomain link is congested. The result is an ongoing dispute during which Netflix users experience bad video streaming quality. So what we need is more internet performance transparency. In other words, we need more visibility into the performance of the various networks that make up the internet. Having more transparency would enable network users to trivially check service level agreements and neutrality regulations. However, transparency comes at the cost of anonymity. In particular, popular anonymity networks like Tor fundamentally rely on limited internet performance transparency in order to achieve their anonymity goals. And this is because at a high level, anonymity relies on hiding the communication patterns of users, while transparency brings them into light. Hence, the goal of this work is to reconcile both transparency and anonymity. But first, let me recap the properties of Tor that are relevant to this talk. Imagine two users, Alice and Bob, that use Tor to communicate with each other. And they do so by exchanging a series of packet counts we call a flow. For example, here, Alice talks to Bob by sending to him a certain number of packets during the first time unit, then fewer packets during the second time unit, and it continues like that. Tor is these three relay nodes in the middle, or equivalently this onion, that provides the following property. An adversary sitting at either position 1 or position 2 cannot tell that Alice is talking to Bob. However, prior work shows that given enough location diversity of the adversary, she can de-anonymize traffic. In this example, if Eve, the adversary, is present at both locations 1 and 2, she can potentially tell with high confidence that Alice is talking to Bob. This is true when Eve sees independent downsampled versions of the actual packet flow at the two locations, but it is also true if Eve does not observe a single flow at location 2, but instead an aggregate, which is a composite of flows, the red and green one here. The good news is that in today's internet, that operates in the absence of any transparency system, it is still reasonable to assume that such a global passive adversary is rare. Let us take a step back. Tor is an overlay over the network of ISPs that make up the internet. We argued that we need more internet performance transparency, so let us explain what is a transparency system and what are its implications on anonymity. Building transparency into the internet fabric boils down to networks like ISPs that publish information about the traffic they observe at their boundaries, and then internet users, regulators, and the networks themselves that uses published information to analyze each other's performance. In particular, if an ISP joins such a transparency system, it would have to deploy special witness logic where traffic enters and exits the domain. You can see that as the orange nodes on the slide. Witnesses observe traffic and periodically send packet reports on traffic aggregates to a logically centralized entity we call the ledger. Upon having all these reports, the ledger and anyone who has access to it can trace problematic behavior to specific areas and check for compliance with service level agreements and neutrality. However, as you might have guessed, by deploying an internet transparency system, we're essentially introducing a powerful global passive adversary. So this talk is about assessing what this new powerful adversary could do to anonymity, and then, given the risk, reconcile the need for both transparency and anonymity. Here is a roadmap of this talk. After describing the metric we use to quantify anonymity, we will assess the risk that a basic transparency system would pose to anonymity. Then, to strike a good balance between anonymity and transparency, we will continue with our solution, which is adjusting the time granularity of the reports. We will conclude with some experimental results and future work. We're considering an adversary who aims to trace the target flow, for example, this one that Alice is using to communicate with Bob. Let's assume that this flow is truly contained in the red and green aggregate. Now, suppose that concurrent to this aggregate, the transparency system publishes two more aggregates, the black ones on the slide. Then, the adversary's goal reduced to determining which of these aggregates are more likely to contain the target flow. The adversary has the following information. She sees the flows pattern, as well as the pattern of each of the aggregates published by the transparency system within the given time interval. What we are searching for is an anonymity metric that has the following properties. If the adversary has no information, or equivalently, if she believes that all three aggregates are equally likely to contain the target flow, anonymity should be high. If, however, is sure that the flow is the correct aggregate, anonymity should be low. If has some information, anonymity should lie somewhere in between these two anonymity points. So far, from what I have told you, it seems that the traditional anonymity set size is the metric we are seeking. This is true, except for when the adversary has misleading information. For example, if Eve is pretty sure that an incorrect aggregate includes the target flow. For example, the bottom one on the slide. In this case, the traditional anonymity set size would give us low anonymity, the red point on the slide, but we argue that anonymity should be high, being the blue point on the slide, because in this case, misleading information is as if no information. Our metric, which we call the T-anonymity set size, addresses all this. You can find more information about it in our paper. Now it's time to assess the risk that the basic transparency system would pose to anonymity. This experiment, as well as any other experiment I'm presenting today, considers real internet traffic traces obtained and made available by CAIDA in 2018. Here we have 50 target flows, each of them being contained in a separate aggregate out of 50 candidate ones. The aggregates are dense in the sense that each of them is a composite of many flows, 512 here. The intuition is that dense aggregates are highly likely to hide the patterns of the individual flows because they simply contain many of them. The basic transparency system we are examining here reports packet counts on aggregates every 1 millisecond. Let us now switch the graph. On the y-axis, we see the cumulative distribution function, or simply CDF. And on the x-axis, we see our metric, the T-anonymity set size. A T-anonymity set size of 1 is the best case scenario for the attacker, who successfully traces the target flow to the correct aggregate. On the other hand, a T-anonymity set size of 50 reflects the worst case scenario for the attacker, because he thinks that all 50 aggregates are equally likely to contain the target flow. As a result, the attacker would like for the CDF of the T-anonymity set size to lie towards the left-hand side, while we aim for the opposite. The orange curve shows the CDF of the T-anonymity set size for the case of 1 second observation time interval. This is simply the time window during which the adversary knows the pattern of the target flow and all candidate aggregates. As you can see, for the case of 1 second, things are pretty bad for the adversary, because now only a few flows have a fairly low T-anonymity set size. However, things change as we increase the observation time interval, from 1 second to 10 seconds, 1 minute, and finally 10 minutes. Because now we can see that the adversary can more and more reliably trace flows. In particular, for the case of 10 minutes, which corresponds to the green curve here, there are about 20% of the flows that are uniquely identifiable. Also, there are about 60% of the flows that are up to 5 anonymous, meaning that the adversary traces them to fewer than 6 aggregates. To sum up, long observation time intervals can result in low anonymity for a number of flows, even in the case of dense aggregates. This brings us to the anonymity transparency trade-off. Today, we have Tor, and if we deploy a basic transparency system, we would have perfect transparency, as shown on this point here. This is because our transparency system can essentially report whatever we like at an arbitrary precision. However, anonymity can be bad, as I have just showed you. Adding differential privacy noise would be one approach. However, we would end up on this left corner, which essentially tells us that the rigorous differential privacy guarantees come at the cost of no transparency. You can find more information in the paper that shows that the straightforward application of differential privacy would not work in our context. And this is not surprising because differential privacy is not meant to be used for verifying service level agreements or neutrality. Hence, the focus for the rest of this talk is how to strike a good balance between anonymity and transparency. However, improving anonymity is not easy, as our solution must take into account 2 more constraints. First, that ISPs must hide all flows, because any of them could be a possible target. For example, for this aggregate shown on the slide, we don't know a priori which of the flows will be targeted. It could be either the red or the green flow. Second, ISPs must make local decisions, because we would like for them to avoid any kind of coordination, because these are different administrative domains. We've seen that if we add performance transparency to the internet and without thinking much about it, there is indeed a damage to anonymity. To alleviate this damage, we propose that ISPs coarsen the time granularity of the packet reports before publishing them to the ledger. Intuitively, what that means is that coarser time granularity better hides the flow patterns because it results in the loss of fine-grained information that would enable a good pattern matching between flows and aggregates. However, it is the very same loss of detail that impacts report utility, because the ledger may now not be able to precisely localize in time certain events, for example, bursts of packet loss. Still, compared to additive noise methods like differential privacy is, the advantage of our method lies on the reliability of the reports it produces. Packet loss rates computed from accurate yet coarser reports will also be perfectly accurate, albeit averaged over longer time intervals. Let me show you how our algorithm operates. On the right, we see the input to the algorithm, and this is packet counts over time for the red and the green flow that make up an aggregate. Observe here that each packet count refers to a single time unit. Now, on the lower part, we see the output of the algorithm. We see again the same aggregate, namely packet counts over time, but now observe that the granularity for some of the reports is coarser than a single time unit. For example, for the first packet count, we see that it refers to both the first and the second time unit merged. The same happens to the next packet count, but then you can see that for the last packet count, it refers to a single time unit. Of course, the question here is how coarse to make the bins. For example, bins that last 1 year may not be so useful in the context of many applications. Given the coarsest granularity we would be willing to tolerate, say 2 time units, the next thing to do would be uniform binning. Under uniform binning, ISPs statically merge packet counts every 2 time units. However, this static binning might not always be the one that hides the most of flow patterns, in which case it also introduces unnecessary noise. What we propose instead is adaptive binning. Given an upper acceptable time granularity, its ISP dynamically decides how coarse or fine-grained the reported bins of an aggregate should be so as to hide the worst of flow. You can think of this flow as a virtual flow, namely a composite of real flows, which has a property that leaks the most across real flows for a given binning. To better explain what I mean, let's go back to the previous example. On the right, we see again packet counts over time for an aggregate that consists of the red and green flow. On the left, we see the leakage for each of these flows. The goal of the adaptive binning technique is to improve the leakage for each flow, and this leakage captures the likelihood that the respective flow belongs to the correct aggregate. Here, we have at least two options with respect to binning. We could bin with the red or the green flow in mind. When binning according to the red flow, our goal translates to hiding the vulnerable part of this flow, which is this packet burst that occurs in the first half of the observation window. One binning that accomplishes this goal is this one. In that case, the leakage for the red flow, you can see that it improves. However, this is not the case for the green flow, for which the leakage may stay the same or even increase, as is the case here. If we bin now according to the green flow, we would get similar results. The takeaway here is that we must co-optimize for both flows, because optimizing independently for each of them may result in some flow left exposed. And this is exactly what we do through the virtual flow construct. The purple binning shows the binning that minimizes the leakage for the virtual flow, which is this one here. And this flow upper bounds the leakage for both the red and the green flow. As a result, if you look at this purple point, both flows leakage benefit from this binning. Now that I have presented to you our solution, it is time to evaluate how this solution improves flow anonymity. The experimental setup stays the same as before. The focus is on the 10-minute observation case that proved to be challenging before, because the attacker could de-anonymize a large number of flows. The graph shows again the CDF of the T-anonymity set size. The green curve corresponds to the basic transparency system we have examined before, and the blue one corresponds to our adaptive binning solution, subject to the constraint that no bin can be larger than 64 milliseconds. There are a few important things we can observe here. First, with our solution, uniquely identifiable flows no longer exist. Second, our solution achieves approximately a 4.4 times improvement for up to 5 anonymous flows, because you can see that there were around 60% of the flows that were up to 5 anonymous before, and we have managed to bring that down to less than 20%. But most importantly, these improvements are achieved at a sub-second granularity. Remember that here the coarsest bin is 64 milliseconds. That means that many applications can benefit from the packet loss rates that our system exposes. In the paper, you can find an extensive evaluation of our algorithm that includes other experimental setups like sparse aggregates, Poisson traffic, and another special type of traffic we call ONO. The results I have presented to you today are representative of these other setups. Also, in the paper, we examined the cost of differential privacy to report utility. And we also show that differential privacy noise would result in packet loss estimates that differ from the actual ones by tens of percentage points. Finally, you can see how our algorithm scales, meaning that our algorithm is deployable. To conclude, if not carefully thought, transparency can greatly damage to anonymity. We also find that adding noise to the traffic reports so as to ensure differential privacy would make the reports unusable in the context of a transparency system. Instead, we propose Morphet, an algorithm that coarsens the time granularity of traffic reports in order to hide the flow patterns that are most vulnerable to tracing. Our solution navigates the anonymity transparency trade-off in an intuitive way and proves to be useful in many realistic scenarios. Of course, there are many other aspects of internet performance transparency we are currently working on, or we are interested to others in future work. For example, whether an alternative solution that leverages ISP coordination would achieve a better trade-off still remains an open question. Also, our ongoing work focuses on the trustworthiness of performance metrics, because to improve their competitiveness, networks may have an incentive to lie and claim better than the true performance. Another aspect of internet transparency also pertains to privacy. However, this time the focus is not users, but networks themselves. Specifically, we are interested in hiding the topology of networks because it is possible to reverse engineer a topology given intra-network path delays trivially exposed by transparency systems. And with that, I would like to thank you, and I'm now ready to take any questions that you may have.
Okay, thank you. And another excellent talk. Thank you very much. I see there was a bunch of discussion in the chat about multipath, and I see Jonathan has joined the queue. I guess, do you want to follow up on that?
I actually was going to ask a different question.
Okay.
Do you consider in your model an attacker who might vary inter-packet times? So like they might try and delay some packets and not delay, I guess, other packets to try and increase the signal?
So the attacker in this setup is not in the sense that he cannot modify the flow itself. What he can just do is observe the packet flow, somehow get access to what does it look like, and then try to find which of these published aggregates that are published at the last hop, for example, here, this is the scenario we consider, is more likely to contain it. So we don't consider more sophisticated attacks where the adversary can also play around and be active with respect to how he can attack the system.
Interesting, thank you.
Thank you.
Okay, thank you. Anyone else have any questions? So I had a question about the complexity of the adaptive binning. Does this get expensive to compute with very large aggregates, or is it still manageable?
Yes. So yes, the complexity depends on the number of aggregates, but not the number of aggregates published overall in the internet, because this is local to the ISP. So yes, it depends on the number of aggregates per ISP, per time interval, of course. But to reduce the complexity and make it run in reasonable time, what we do is that we split the time into intervals around the algorithm independently for each time interval. So because this is the parameter that mostly affects the cost of the algorithm with respect to runtime, not the number of aggregates.
Okay, thanks. And my other question was, how sensitive is this to correct implementation of the adaptive binning? Does it degrade gracefully if people do this slightly incorrectly, or does it fail catastrophically?
You mean how important it is to use a particular algorithm to do the binning?
Yeah, or if I guess if the binning isn't quite implemented right, is it really sensitive to getting the precise binning correctly, or is it? To
be honest, not so much. There are benefits to using this algorithm, but for example, we consider a variant of the algorithm where the ISP would maybe statically merge every, let's say, 10 time units, and there are still benefits doing that to having no deployment, no algorithm deployed at all. So it's not that crucial. But still, coarsening the time granularity is crucial, yes.
Yes. Okay, great. Thank you. All right. Does anyone else have any questions for Georgia?
I think there are some other questions on the chat, but I can take that offline. Or...
we have time if you want to answer them. If you want to answer them live.
So Jonathan, I think he's asking. I think he's thinking whether it would be better to use game theory or auditors. So Jonathan, would you like to clarify what do you mean by game theory here, or auditors?
Yeah. So I was just thinking, like, because I assume you also have to measure traffic between ISPs, and so you could somehow have it that ISPs would also talk about what happens between ASs. That's the right grouping. But basically the idea would be one ISP lying makes other ISPs look worse or better, or presumably worse. And so you could have it such that the ISPs would be honest because they're worried about their competitors making them look bad. So there just sort of has this prisoner's dilemma style, like we all have to work together or else we'll all look bad.
Yes, that's actually, it's really great that you brought it up. It's something that I'm currently working on. Our current work is exactly on the honesty of ISPs. So, but this is a bit of orthogonal to this paper. So this talk I talked about today, it was about, let's assume ISPs are honest, and let's take this, let's make this assumption, and then try, given that it is in their benefit to protect the privacy of their users, how would they try to hide, how would they report these packets, would they report in order to hide who is talking to whom. However, like what you mentioned is really a great topic. Why would the ISPs ever be honest to us with respect to what they do with packets? Why? Because if I am an ISP, I would rather say that I'm doing fine, I don't lose any packets and I'm not delaying any packets, and blame my neighbors. However, in our current work, we actually show that yes, we model that with game theory, you are completely right, and we show that there are incentives, given that users have care about certain metrics, like packet loss, for example, the ISPs, we form a theoretical game, where ISPs publish the reports, and based on what they publish, we're able to detect inconsistencies. And we argue that they wouldn't like to be inconsistent because this is bad publicity, because they are connected to their neighbors and no one would like to enter such kind of disputes. For example, if you think about packet loss, let's say we have two only ISPs in the internet. We know, and the ends, we assume that the ends know how much packets how many packets are lost, then it has to be that either the first or the second ISP lost the packets. So in that case, it couldn't be that nobody lost them. So if I am the first ISP and I'm losing the packets, then if I claim that I do not, it's as if implicitly I'm blaming my neighbor. So we argue that these kinds of incentives do exist, and ISPs wouldn't actually like to enter such kind of disputes. Thanks for the question.
Super interesting. Thank you.
Thank you. So yes,
thank you.
To add to this, so our ongoing work explores what kind of metrics we can incentivize the ISPs to report honestly, and we can show that at least packet loss, mean packet loss, and also mean packet delay and variance of delay, these metrics we can do expose in a trustworthy manner. Thank you for the question.
Okay, thank you. I don't see anyone else in the queue, so thank you again. Great talk. And I guess we'll move on to the final talk, which is Renisha, who'll be talking about her paper, Beyond Jane's Fairness Index, Setting the Bar for Deployment of Congestion Control Algorithms. Renisha Ware is a fourth-year PhD student in computer science at Carnegie Mellon University. Her current research focuses on challenges arising from the deployment of new transport protocols and congestion control algorithms in the internet. Okay, thank you.
Hello. So today I'm really excited to talk about this joint work with Matt, who's now at Nepheli, and Justine and Trini, who are my advisors at Carnegie Mellon. And my name is Renisha Ware. So today I'm going to talk to you about this work on congestion control deployment. So let me start by motivating why we care about this and why you should too. So we want to answer the seemingly simple question: if you design a new congestion control algorithm Taco, how do you show that Taco is reasonable to deploy in the internet today? Well, typically we try to say a new algorithm Taco is reasonable to deploy in the internet if it fairly shares with widely deployed legacy algorithms pair. For example, here are a bunch of graphs and tables all trying to use fairness to make the argument that their algorithm won't be too aggressive towards the status quo, which today is typically regarded to be cubic. But here's the thing, everyone falls short of actually achieving fair outcomes. But everyone still has to try to make these arguments that their algorithm is deployable. So let's look at some examples of what these arguments look like. So I don't want to dig into the graphs here, I just want to draw your attention to the arguments. So in the cubic paper, they show results where cubic is unfair to Reno, but argue that this is outside of the TCP friendly region and that this doesn't highly impact Reno's performance, whatever that means. And in early presentations on BBR, Google showed that BBR v1 was unfair to cubic in shallow buffer networks and basically said they'll fix it in later versions of BBR by modeling those shallow buffer situations. PCC Vivace also showed it could be unfair to cubic, but argued that as the number of cubic senders increases, it achieves the best fairness among new generation algorithms. And COPA makes a similar argument that it's much more fair than BBR and PCC, and it uses bandwidth that cubic wasn't going to use anyway. So I highlight all of these arguments here to drive home this point that in practice, we rarely can or even want to achieve fair outcomes, because it turns out fairness is either too restrictive or impractical. Consequently, everyone ends up just sort of having to make these excuses about why their algorithm is still reasonable to deploy despite having unfair outcomes. And it's really unclear if these excuses are okay. So the problem is we're basically left with no real bar or threshold for what makes a new algorithm safe or reasonable to deploy in the internet today. So in our paper and in this talk, we argue for the need for a practical deployment threshold. That is a bound on how aggressive any new algorithm, which I'll refer to as Taco throughout this talk, can be to any legacy status quo widely deployed algorithm, which I'll refer to as pair in this talk. So the outline for this talk is as follows. First, I want to describe for you the desirable properties for a good deployment threshold. Then I'm going to define a new deployment threshold based on harm, which unlike fairness has all of these desirable properties. So let's jump right in and start by discussing what are the desirable properties for a good deployment threshold. Well, in our paper, we identify 5 such properties. We say a good deployment threshold should be practical, multi-metric, status quo biased, demand aware, and future-proof. So those are just a bunch of words that don't mean anything to you yet. So let's start by defining what we mean by practical. So we've already seen that a threshold based on fairness just is not practical, right? Because no one can actually achieve fair outcomes. Therefore, a good deployment threshold needs to be practical in that it should actually be feasible in practice for a new congestion control algorithm to meet the threshold. So that's what we mean by practical. Next, we say a deployment threshold needs to be multi-metric. So let's illustrate what we mean by multi-metric through an example. So consider the scenario where, let's say Beyonce is at home. She's trying to talk to her daughter, Blue Ivy, over Skype and over her home Wi-Fi access link. And let's say her access to the internet is really slow. So her access link is a slow bottleneck link here. And let's say it's using some new algorithm pair. Let's say it's using some old legacy congestion control algorithm pair. Now, let's say base connection using pair is able to achieve about 5 megabit per second throughput and a good low latency. So this is when it's not sharing the bottleneck here, it's just alone. But now let's say her husband Jay-Z comes home and he wants to download the Windows operating system for some reason. So this is going to be a large, long-running download. And the server he's downloading from is using some brand new congestion control algorithm, Taco. Now let's say Taco is able to use the rest of the available bandwidth, but that this comes at a cost. and base latency is going to go way up, so maybe now her video quality is terrible. So the impact on latency matters here as to whether or not we would say it's acceptable to deploy Taco in an internet with a ton of latency sensitive applications using pair. Therefore, it's important that a deployment threshold be able to consider a variety of metrics beyond just throughput. So metrics beyond just throughput are becoming increasingly important in the internet today when we have more and more applications that care about things like latency or jitter or loss rate. However, we can never really talk about anything other than throughput when we're stuck talking about fairness. So we're used to thinking about deploying algorithms as if the network is a pie that we're cutting up to share, but that doesn't make sense for performance metrics like latency, loss, or jitter. So that's what we mean by multi-metric. Now let's walk through an example to illustrate what we mean by status quo biased. Now, let's say Beyonce is downloading the Linux operating system from a server using some popular legacy algorithm pair. So this algorithm, let's say it works well in Wi-Fi networks, so her download speed is just using all of the available bandwidth. Jay-Z comes home, he's still downloading Windows, and the server he's using is using some new algorithm Taco. Now let's say, unfortunately, this time pair is too aggressive. And so Taco is only able to get 1 megabit per second throughput, while Beyonce still gets 9. So in this case, though there is imbalance, I would actually say it's perfectly acceptable to deploy Taco alongside pair, right? This is because the currently deployed legacy algorithm pair is the one being too aggressive towards the new algorithm Taco, not the other way around. So when it comes to deployability, we don't actually care if the new algorithm is the one being hurt. Thus, a deployment threshold needs to be status quo biased. It should only be based on the impact that Taco has on pair and not vice versa. As an example, James Fairness Index is not status quo biased, right? James Fairness Index would assign the same score if the new algorithm was one being harmed as if the old algorithm is the one being harmed. So it can't distinguish between these two scenarios, so it's not status quo biased. So next we say a deployment threshold should be demand aware. Let's illustrate demand awareness through what? An example. So now let's say again, Beyonce's trying to download this large file and the server uses some legacy algorithm pair. But now let's say pair really sucks at fully utilizing all of the available bandwidth in a Wi-Fi network. So she's only getting a download speed of 3 megabits per second. So now Jay-Z comes along, trying to download that Windows OS still, using some fancy new algorithm Taco. Now, let's say Taco's much better at utilizing the available bandwidth in this Wi-Fi network, but it's able to do that without hurting Bay's connection. So it's able to just use the rest of the available bandwidth and get 7 megabits per second. So here again, it's perfectly reasonable to deploy Taco because it's not hurting Beyonce's connection at all. Although they're not equally sharing, Taco is only using bandwidth that pair wasn't using anyway. So this is what, so a good deployment threshold should not penalize Taco when pair already has inherently poor performance. This is what we mean by demand aware. For example, maximum fairness, which accounts for the demand of a flow, is demand aware, but equal rate fairness, which just says each flow should get the same rate, is not. So lastly, we say a deployment threshold should be future-proof. So by future-proof, we just mean that a good deployment threshold should be useful on a future internet where none of today's current congestion control algorithms are deployed. So we care about this property because many discussions around new TCPs considered something called Tcp Friendliness. So Tcp Friendliness focuses on behaving just like Reno to be fair to Reno, even though very few senders on the internet probably even still use Reno anymore. So I'm going to give you a little silly toy example that explains why it's really silly for us to keep binding ourselves to Reno. So consider this example where in the past, Skype and a bunch of other services used some algorithm Tomato. But let's say Tomato was terribly inefficient. So today, Skype, along with many other services, switched to using a much better algorithm, and they're now using pair. Now, when Taco comes along, does Taco need to be nice to pair and Tomato, or just pair? Well, if no one uses tomato anymore, new algorithms only need to be nice to pair, whatever the current status quo is. So this is what we mean by future-proof, that a future-proof threshold would only require taco be nice to pair, whatever the current status quo is. So I say all of this to make this point that traditional notions of TCP friendliness are just not future-proof. In a future where no one uses Reno at all, we should not be relying on thresholds bound to Reno or any other particular algorithm's behavior. So these are the 5 properties of a good deployment threshold. So next, I want to define a new deployment threshold based on something we call harm. So let's begin by motivating this. So when we're trying to show deployability, we typically run experiments where we have pair, whatever the current status quo is, versus taco, our new algorithm, and we want to measure performance. So if we care about something like throughput, that might look like this, right? So we have pair's performance, we have taco's performance, and fairness would say compare these 2 bars. So you want to say, is this outcome fair or not? But remember, because of status quo bias, we don't actually care what happens to taco's performance when the 2 compete. We only care about what happens to pair's performance. In particular, if this was pair's performance alone, we care about how pair's performance has changed now that when it's competing with taco. So comparing this red and green bar. So this leads to the proposal in our work, which is that a deployment threshold should be based on how much harm taco does to pair. So let me illustrate what we mean by harm with an example. So again here, Bay's trying to do her video conference, and let's say that pair is able to use all of the available bandwidth and gets low latency when pair is alone. But now, when Jay-Z comes along with his taco flow, Beyonce's throughput goes down and our latency goes up. So here we would say that Jay's connection has harmed Beyonce. So let's be more sort of formal about our definition for harm. So harm is measured between 0 and 1, and like Jane's fairness index, it's measured between 0 and 1 like Jane's fairness index, where 0 is harmless and 1 is maximally harmful. So our harm function takes 2 inputs. The first is x, where x is pair's solo performance. So this is pair's demand. And it takes y, where y is pair's performance when it's competing with taco. Thus, to compute harm for more is better metrics like throughput, harm is x minus y over x. And for less is better metrics like latency, harm is y minus x over y. So in this example then, taco causes 0.5 throughput harm to pair, and taco causes 0.95 latency harm to pair. So you should be able to see that harm is multi-metric, right? I can compute throughput harm, latency harm, jitter harm, loss rate harm, whatever other kind of metric I want. It's also status quo biased, so the 2 numbers in our harm calculation are only based on pair's performance. I don't care what pair's performance is here. And it's also demand aware. So here we define the demand as pair's solo performance. So harm gives us a way to talk about taco's impact on pair's performance. But I haven't said how much harm is okay. So for this, we need a harm-based deployment threshold. And our key proposal in our work is that a harm-based threshold should be the following. Taco should not harm pair much more than pair harms itself. So that is, any new CCA shouldn't harm the status quo more than it harms itself. So what do we mean by much more than? Well, so far we've computed the harm that taco does to pair. And now we want to compare the harm taco does to pair to the harm pair does to itself. And say, how do we compare these 2 things? So in the paper, we discussed 3 possible ways to compare these. But today, I just want to discuss one possible threshold, which we call equivalent bounded harm. And equivalent bounded harm, just like its name, says these 2 things should be equal. So the harm taco does to pair should be equal to the harm pair does to itself. So returning to our previous example, we looked at what happens when taco competes with pair, and you can see a certain performance. And we compare that to pair's solo performance to compute the harm that taco does to pair. And now we have the same scenario, but with pair versus pair, and we get certain performance outcomes. And we want to say, what's the harm that pair does to pair? So let's go back to our harm calculations to compute this. So before, this is what the harm that Taco did to pair. And now we want to add in what's the harm that pair does to pair. So here you should see that the throughput harm is the same because I get the same throughput for pair when pair competes with Taco and when pair competes with itself. So under equivalent bounded harm, Taco would be okay. But if we look at latency harm, it's clear that Taco is much more harmful to pair than pair is to itself. So under equivalent bounded harm, we would not consider Taco deployable. So a harm-based threshold is practical. We can already see that pair can achieve certain performance when it's competing in practice with pair. So it should also be possible for Taco in practice to get similar performance outcomes. Certainly if pair can do it, then so can Taco. And it's future-proof, right? There's no baggage here. There's no tomato here that I'm trying to behave like. The only thing that matters is what is the status quo and how does it compete with itself. So if tomorrow the status quo is banana, then that's what we would compare against. So is equivalent bounded harm like the perfect deployment threshold? Well, it certainly meets all of our criteria as we previously discussed, while alternative thresholds based on fairness or Tcp friendliness certainly do not. So it's better than what we had before, but we do have some concerns about equivalent bounded harm. So let me show you a little example. So here I'm illustrating an issue with equivalent bounded harm where let's say when pair competes with pair for 2 long running downloads, one flow gets 7 megabits per second and the other only gets 3. So there's significant imbalance here when pair competes with itself. And under equivalent bounded harm, any new Taco algorithm couldn't improve this imbalance, which seems problematic. So this is a hotness paper and it's an open question what's exactly the right harm-based threshold. And in the paper, we defined 2 other thresholds that allow Taco to take a little bit more bandwidth, but we're not sure what exactly is the right threshold. And there are other open questions in the paper. For example, when you run performance experiments, there are of course going to be a distribution of these results. So should we care about the average, worst case results or something else? Also, we can't possibly measure the performance of pair versus Taco in every possible scenario. So we ask what are the right workloads and networks we want to test for deployability? And even if we have a threshold, can we really even enforce it? So while we haven't exactly settled on the perfect threshold, here's what we do believe. Fairness is wrong. It's not working as a practical threshold. And thus, we need to stop making excuses for why our new algorithms are not reaching an unrealistic goal like fairness. And lastly, reasoning about harm is the right way forward. And it's going to give algorithm designers a much more realistic goal. So that concludes this talk. Please look at the description box for a link to the paper. And if you have any questions, please shoot me an email or ask me a question on Twitter. And thanks for listening.
All right, thank you. Excellent talk. Thank you. Welcome, Renisha. I know it's a terrible hour of the day for you.
It is.
I see a bunch of questions on the chat. Does anyone want to jump in at the microphone line? Surely someone must do. While we're waiting for that, I mean, Brian, go ahead.
Yeah, while we're waiting for that, go ahead with your question. I'd like to hear which one you came up with, because it might be the same one.
Okay, I was going to ask about. I mean, you know, you mentioned some limitations, some other open issues. I was just going to ask if you've done any more work since. I mean, that this is a paper from a year ago. If you've done any more work to address those open issues, and if you'd like to say anything about that.
So we have a project where we're trying to actually apply, like use a harm-based threshold to show whether or not applications we see in the wild are fair. And so while doing that work, we've like tried to refine what we mean by like if equivalent bounded harm is the correct thing, or in the paper there's like other ones, symmetric bounded harm, worst case bounded harm. I guess my work's kind of focused on how do I actually use this harm-based threshold to say something in practice. Yeah, that's sort of the.
Okay. Seems like a great thing to do. Yeah.
Okay,
Brian.
so hi, Brian Trammell. I'm not going to ask you any difficult questions because it's like what, it's 4 in the morning there, which is
it is 5:30.
5:30. Okay, that's still terrible. Thank you very much for this talk. Like, you know, looking at your last slides, I think there's been like wide consensus that fairness isn't cutting it in the community for a very long time. But that just went into complaints. And this is actually sort of like, okay, we're going to address the complaints. I would, yeah, not my research group, but I would invite you to try and find a way to come to the Internet Congestion Control Research Group at IETF110. And I would hope that we could have sort of a long open discussion about how to actually use harm as a metric to talk about measurement of some of the work that's being done there. I think that you know, that's a really good room to actually sort of expand the applicability of this metric. I need to think about, you know, some of the, you know, the questions about setting thresholds here and exactly how you would take this dimensionless metric and compare it to other sort of like the benefit side, because now we have the cost side and we can talk about the benefit side, and that actually kind of changes the ability to reason about this in a multidimensional space, which is super exciting. And I'd really like to see that followed up on in ICCRG 110, which will be in March online in a European time zone. So still not great for Pittsburgh, but much less bad than this time zone. So hopefully we can make that happen, and I look forward to talking to you there.
Yep. Next is Jake, I think.
Hi. Thank you for this talk. I would put this at my favorite talk in the last decade, at least.
Wow. Thank you.
And so I would be very, very interested to see a sort of example walkthrough, and I think we have a couple of very relevant natural experiments from recent history. One of them being you know, just I would love to see like how this is quantified as the harm of cubic to Reno. This is a thing that actually sort of happened. And also the harm of Reno to Vegas, for example. Like if we think about, you know, sort of the early history of when congestion collapse was the urgent matter that sort of drove the deployment of Reno, and Vegas happened within that year, but kind of got, you know, we know from some of the early Vegas papers that it didn't get deployed because it loses so badly to Reno, right? So like in a sort of counterfactual world where we had managed to land on Vegas, which is better for everyone, but tried to deploy Reno, like what would that harm have looked like? Because you know, having worked with some congestion control, you know, in practice on the internet, like dealing with the loss-based congestion control approach as trying to deploy a delay-based. I was working with fast TCP and fast for some years before we were acquired, and that yeah, it would be nice to know sort of like we felt this impact constantly, and having a quantifiable value for like how bad was it that we adopted Reno. I would be very interested to see that analysis, regardless of you know, how useful it is going forward, but just sort of as an example of how to apply this research. Thank you.
I like the idea of counterfactual alternate histories of the internet. We should look into that. Rod.
Thanks. That was a great talk. I mean, everybody's saying it, but it really was. My work these days is on quantum networking, and we're doing some simulation. And one of the next tasks, one of our big tasks that's at hand, is actually comparing multiplexing schemes. So we're looking to compare time division multiplexing versus stochastic multiplexing and buffer memory space multiplexing and things like that. Can your measures be used for comparing multiplexing schemes or OS scheduling schemes as well as congestion control?
I don't see why not. I mean, all you really need to have is like a scenario where you have some status quo and you want to compare, does this new thing harm the status quo? So as long as you have that, then yeah.
Yeah, in the case of multiplexing, it's going to be, so presumably the schemes, when we're comparing things like TDM versus statistical multiplexing, it's going to be more of comparing one simulated network scenario using one versus the same network simulated using the other. And so it would be two different scenarios rather than competing in the same network, most likely.
Oh. Then I'm not so sure.
Off the top of my head, I think there's probably a way to do it, but I haven't thought about it a lot yet, and I don't know how. So I was wondering if you had thought about other uses of congestion control.
Yeah, the idea here is I have these two things competing in the same network, and I want to see if one thing is harming the other.
Okay, thanks.
Okay, thanks. Jonathan.
Yeah, so my colleague Pete Heist and I are already working on test suites to help with our congestion control development process. And we are planning to incorporate this harm metric into it now that we know about it. And it makes a heck of a lot of sense. So it occurred to me from the discussion just now that possibly our test harness or something like it would be helpful for examining these counterfactuals. So maybe we can discuss that at some point.
Okay.
Yeah, I mean, there are a bunch of a bunch of people building test harnesses. It would be great if there was some way of integrating these ideas into those, so we could automate some of these metrics. Bob, I think you're next.
Hi. I wonder if you've thought of the situation where let's give a numerical example. Where we talk in terms of bytes instead of bits per second. So let's say a 100 gigabyte flow starts at the same time as a say a 10 megabyte flow, and then 10 seconds later another 10 megabyte flow starts, and then 10 seconds later another 10 megabyte flow starts, and so on. So you've only got two of the flows running at any one time, but you've got very reasonably small, but still large 10 megabyte flows running against this much longer flow. So overall, all the 10 megabyte flows, if they all got equal bit rate sequentially, then by your harm metric, they would be perfectly fair, or there'd be equal amounts of harm. But if the larger flow that goes on longer and hits all the other flows were to go slower every time one of the other flows was there, and the other flows that were shorter were to go faster, they would all complete earlier, and then the larger flow would also complete at the same time. So the point there is that bits per second is not the right metric in the first place to measure the harm, because you have to look at the length of the flows as well.
Okay. So my definition for harm and everything says you can use whatever metric you want. It doesn't have to be.
I know, but that's the point. You have to use the right metric, and all the examples people are thinking of think you can use any metric, but you can't use any metric. You have to use the right metric to measure harm in a particular situation. That's my point.
Sure.
Yeah. And the problem is people are measuring this with bits per second. That's the problem in the forum we're in, the IETF, that people don't realise that there's another dimension here. That it's time. I'm not saying it's not useful to have your harm metric. What I'm saying is that we also have to be careful which actual unit we use to put into the dimensionless equation. Yeah.
It sounds like you're saying we need to be careful about which of the particular metrics we choose, and to think about what's appropriate metrics for different applications to compare them.
Yeah, but in that scenario, you can't know what was useful to those flows, whether it was completion time or whether it was bit rate, when you're just looking in the network. That's the problem. Anyway.
Yeah. It has to be treated at the end.
There's a lot of literature about this, but just to explain to people, it's not just equal bit rate, or it's not even equal harm if you're measuring bit rate.
So I think that will need to be incorporated into various test suites, so that these different metrics of harm are automatically generated, so that they can be evaluated all at once.
But my point is that looking from the network at that situation, you cannot know what is important to each of those end systems. You don't know whether it's completion time or bit rate. Sure. So you can't measure the harm from the middle of the network.
Sure.
And so this is why it's important to measure the congestion that they all cause, and use that as the metric.
Yeah.
Anyway, this requires a deeper conversation than we can have here, but yeah, thank you very much.
It sounds like we should move this to the ICCRG list or somewhere. Yeah. But yeah, thanks. I think the metrics that the harm metric can cover this. It just needs to be applied correctly. Sylvester.
Hello. Thank you for the excellent paper and talk. I really liked your paper last year when I read it. And still, did you do any kind of comparison, for example, cubic and BBR, or any two congestion controls? Because I still have the feeling that the harm-based bar is a much better bar than, for example, James Furness, but it's still close to impossible to meet and innovate at the same time.
I'm sorry, I'm confused by what's your question.
Okay, did you test your harm-based threshold with actual congestion controls over the internet? And did you find that for example, a new like cubic is really fair to Reno or not, or whether BBR is fair to cubic or not? Because I still have the feeling that for every new congestion control and old congestion control bar, you can easily find scenarios when this bar is not met.
Yeah, so we're actually working on that now. And yeah, it depends. We found it depends on the application. So we've looked at things like just long running downloads, but also video, and compared if you have two video applications, and let's say you care about bitrate as your metric, just using, having cubic and BBR compete, this performance degrade, and I'm not remembering the findings off the top of my head, but we'll see that in the future when I finish that paper.
Okay, thank you.
Excellent. Jana, you get the last word.
Oh, hello.
Hi, Ray.
Hello.
Thank you for presenting this work here. I have long wanted this work to show up in one of the IRTF places, and I'm glad that you showed up here. So I want to see if I can try and articulate what Bob was trying to say, because I think what Bob was trying to say is actually something that's actually quite important. On the one hand, I think that what your work is doing is challenging people to move away from notions of fairness, notions of thinking about flow fairness, flow level, or bitrate level fairness. On the other hand, there is a risk. And the risk is that now people get attached to what I would think of as a similarly constraining or ossifying notion of flow level harm. So if one simply thinks of bit rates, then you effectively end up with a dual of the previous problem, right? You're simply thinking about harm now, but in a very sort of micro benchmarky way still. So the fact that you moved away from fairness is helpful, but the problem is that one gets still stuck to being with micro benchmarks. But I know that that's not what you're thinking, but I think that there's a risk in simply having a metric and thinking that now that we have this is the one true way of measuring congestion control usefulness. But to your point, and I think you've said this in other places, that it is important, you said this earlier to Sylvester as well, that it is important to consider the impact on other applications. So ultimately what matters is the metric that applications use to determine what usefulness or useful work is for them. And that tends to be quite difficult, and that tends to be moving. Like, I mean, there's today, YouTube has a certain way of doing things, and therefore certain metrics become important. Tomorrow it's something else, it's gaming, or it's, I don't know, it's Twitter or it's TikTok or whatever it is, and they have different metrics. And as network use changes, we will find that there are metrics that get more or less harmed for the same set of congestion controllers. And that's something that we have to keep in mind. And I think that we want to be mindful of not, we want to be mindful that we can't find a silver bullet here. There isn't one, really. But there is a process that one can think about how to evaluate a congestion controller in a better than we've done in the past for a set of circumstances that happen to be true today. And we might want to reevaluate this in the future, because as circumstances change, as application workloads change, the notion of harm from an application's point of view will change. And I think that's important to keep in mind as you work on this. I just encourage you to think about it that way as well.
Thank you.
Okay, thank you, everybody. Thank you again to all the speakers. Congratulations to all the prize winners. I think this has been an absolutely great set of talks. So thank you and congratulations again. I'd like to remind everyone that the deadline for next year's for nominations for next year's ANRP is this Sunday. So if you want to get talks this good next year, please nominate some good work and go to the IETF.org/ANRP site and nominate the work. And with that, that's everything we have for today. Thank you, everybody, and I hope to see you in person eventually, but online in March, if that's what we can do. Thanks, everybody. Bye.
Make good choices.
Go get some rest, everybody. It's been a long week.